Hi everyone. In this video, we are going to connect the concepts of resonance and expanded octets. We can actually use resonance theory to come up with more stable structures that exceed the octet for period 3 elements and below. So the easiest thing to do to illustrate this is to look at an example. So let's take SO4 2-, the sulfate anion. If we count the number of electrons and draw the Lewis structure, sulfur brings 6 electrons, oxygen brings 4, there are 4, brings 6 electrons each, so that's 24 electrons total. And the fact that we have a -2 charge means that we will have 2 additional electrons from that, so this gives me 32 electrons to work with. I would build my framework. Sulfur is the least electronegative, so it will be the central atom. And I've used 8 electrons, so I have 24 electrons remaining to place as lone pairs. And since each of the oxygens will have 6 electrons in 3 pairs each, there are 4 of them, so that means 24 will be used, and we'll be left with 0. When we calculate our formal charge on sulfur is equal to the group number, 6, minus the number of bonds, plus lone pairs. So this equals +2, so I'll go ahead and add that there. And the formal charge on oxygen is equal to its group number, 6, minus the number of bonds, which is 1, minus electrons in pairs, which is 6. So I will get a -1 charge on each of the oxygens. So this would be the Lewis structure that we come up with following those rules. And it doesn't look particularly good. We have more than 2 formal charges, which is a general rule we don't want. There are some exceptions to that, so it is okay in, say, the nitrate anion, NO3-, to have more than 2 formal charges, but generally we want to minimize formal charge. And this having 5 charge centers, I would not call minimized. So there are 2 schools of thought here. Is formal charge more important, or is the octet rule more important? So people on the side of the fence that say the octet rule is more important would say that this structure is fine and dandy, good to go. I am on the other side though, where I think that formal charge is more important, and it is more important in organic chemistry, so we're going to work at minimizing formal charge and exceeding the octet where possible. So we look at this structure and we start to think about the things that we could do to minimize formal charge. As we saw before, we can move lone pairs to form multiple bonds between atoms. So as an example, I could take this lone pair and move it to form a second bond between the sulfur and the oxygen. And this is a type of resonance, and I'm noting that with the double-headed arrow there. And I can do this because sulfur is in period 3 or below and can exceed the octet. So by doing so, I can recalculate formal charge. I would find that I have now reduced the magnitude of the positive charge here and now no longer have a negative charge on the oxygen. So we went from 5 charge centers to 4 charge centers. So that's an improvement. We could imagine doing this again, right? So we could add a lone pair to the sulfur as a multiple bond. And this gives me the structure. And if we check formal charge, it would be neutral, okay? So we've gone now to just 2 charge centers. So much, much better. Then could we do it again? All right, so can we take another lone pair and put it on that sulfur atom? Let's do it and see what the result is. So now we would end up having a negative charge on sulfur because it has 1 more electron than it brings to bond with. So then we could assess the stability of these. Since they both have 2 charges, they're both negative charges, we have to look at what atoms bear those negative charges. So oxygen bears both of them in the top structure, and we have oxygen and sulfur bearing one of them. Because oxygen is more electronegative, it's going to be happier with that negative charge. So the structure that I've drawn here below is not going to be particularly good. There's no advantage to forming that second bond, so it won't. Okay? And then we can, of course, rank the other contributors in terms of their stability. We already said that this has too many charge centers, more than 2. It's out. This also has more than 2. I'd say that it's out. So this is going to be the best structure that we can represent the sulfate ion with. And I'll tell you that there are a total of 6 resonance contributors for the sulfate anion. So there's this guy, plus 5 other structures that you can draw. So I challenge you to draw those out right now, if you have a chance. If we draw out all 6 of the resonance contributors, we can come up with a hybrid. And the hybrid would show me that the sulfur-oxygen bond is somewhere between a single and a double bond. So we'd have negative charge on all of these oxygens. All of the contributors are equal to this hybrid structure, so we can actually calculate the bond order here. We have these 2 pi bonds shared over 4 centers, so 2 pi bonds over 4 bonds is equal to 1/2. The bond order for the SO bond is going to be 1.5. And if we look at the experimental data, we do find that the bond length is between that of what we would predict for a sulfur-oxygen single bond and a sulfur-oxygen double bond. So again, we agree with the experimental evidence here. When possible, we will exceed the octet by using resonance theory to move electrons and form additional bonds. This can only happen for atoms in period 3 or below. So sulfur is an example, phosphorus is another common example that you'll see. If you have any questions, reach out, you know where to find me. Thanks for watching.